this talk will hopefully be useful for you, because it is an introductory talk that will introduce this library called CATS to you, and more importantly, it will show you the main ideology and idea, the paradigm behind the programming in CATS. So the plan of our today's talk is, first of all, we will be talking about the problem of side effects while programming imperative programs, why they are bad. Then we will have a look at how this problem can be solved by the concept of effect types. Then we will see how naturally the concept of monads arises from programming with effects types. Excuse me. Can I take this mic off? Yeah, okay. It is more convenient. So we will have a look how the concept of monads naturally arises and becomes required when we are programming with effect types in this manner. After that, we will see how the need for monads generalizes to the need for type classes in general. We will introduce the notion of the type class, what it is, and why it naturally is required when programming with effect types. And finally, for all of these examples, for all of these topics, we will be looking at the practical introductions, practical examples in Scala, so that we know why, how they arise from practice. So first of all, a few words about myself. Currently, I have 5 years of experience programming in Scala. Currently, I'm doing programming and consultancy for my company Functor Tech that specializes obviously on purely functional programming. And also another direction of our company is educational materials and trainings. So I have authored a number of training materials like courses for Pact Publishing and for Functor Tech independently. So first of all, a few words about purely functional style, what it entitles. I think probably most of you know already these topics that are displayed on this slide. These are the concepts from the purely functional style, what you need to know in order to program in the purely functional style. First of all, it is immutability. So mutability is bad. Mutable variables are bad. We tend to write programs in an immutable style. Also, we aim to eliminate side effects. And on side effects, we will be talking much more today. And finally, it is referential transparency. It means roughly that the expression can be rewritten to the result of its evaluation, and the semantics of the program will not change. So if you have a function call, you can replace it with the value to which this function evaluates, and nothing in the program will change. So in this presentation, we will stop in details on the problem of side effects and why functional style tends to eliminate side effects and why they are bad. So first of all, a little demo. So here I have the program, which is a mock database program. So assume we have a database, and we have some users in this database, and for example, it is a blog database. So we will have also some user posts in this database. We can emulate, we can mock this database with the following interface. So this is the interface database, and it has, oh, sorry, I meant to show you this code. So we can emulate this database with the following interface. So it is effectful database. Obviously, this current demo is intended to display the side effects and why they are bad. So it is an effectful database. And it is emulated in a very simple way. So the function accepts the user ID, and it is supposed to retrieve the user object, which is an ordinary case class from the database. And if the user ID is in the supported domain, in our case it is emulated as 42 and 100, then the user is returned. Otherwise, we have nothing to return. And a standard solution that is used in languages like Java, for example, an imperative language, the standard solution is just to return a null pointer. So This is something that we try actively to avoid in Scala, and here is why. Also we have this capability to generate this trait, effectful database. We have a companion object of the effectful database trait that is needed to establish the connection to the database. And here the connect method is intended to emulate the situation where the database is not online. So we have this switch database online over here to emulate the situation where the database is not online and we cannot establish the connection. So if it is not online, if something goes wrong, the standard way in Java, in imperative languages, is to throw an exception. So here it is thrown over here. Now let us see how this scenario plays out in a mock scenario when we need to connect to the database and then get some users from the database. So here we have the situation where the database is connected successfully because we emulate the situation where the database is online, and we are trying to get the users that does not exist. So the user 10 is not in the list of the users that are allowed to be returned. So how will it play out? So if we run this program, it is fifth over here, we get a null pointer exception. We get a null pointer exception because we are trying to print the user ID and the user is null. So why is this bad? It is bad because the capability of the program to return null in that situation in this line is not reflected in the signature of the function getUser, and hence the compiler has no way to warn us that we are about to perform a potentially dangerous action. As a result, we need to keep in mind that the function getUser might return null. So it is an added mental load to the programmer, because the programmer cannot see from the signature of the function that it may return something that is out of its return type. So null can arguably be said that it doesn't belong to the domain of all possible users. It is something completely different, because when we call getUser, because when we call ID on null, it throws an exception. It is not a user. Also, if we emulate the situation where the database is offline, so database connect is false. If we emulate the situation over here, we get the runtime exception of database is offline. And again, it is bad because on the 19th line, nothing warns us that the exception might be thrown. So in Java, we are forced to declare exceptions in the function signatures. But in Scala, we do not have this requirement. So the exception can be raised in the function, and we have no way of predicting that it will be risen. And hence, we might forget to handle this exception. And hence, we increase the probability of bugs, because there is an increased probability of the behavior that we could not predict. The compiler does not warn us about these situations. So, given this example, let us conceptualize side effects. So, a side effect can arguably be seen as a set of instructions within a function that affects the environment outside this function. So, in our examples, in the first case, we have, in the case of getUser that returns a null, we have the instruction of returning a null that affects the environment outside the function. Affects it in which way? In the way that we expect that the function connect.getUser will return us a user, and we will be able to call all the methods that are available on the user, which is ID, because the user is defined simply like a case class over here. But we are trying to call this method ID on the user, and we are getting a null pointer exception. This means that the instruction from within the function has affected the environment outside the function. It is even simpler with the exceptions, because when we throw an exception, the program breaks at the point where you throw an exception if you do not handle it. Hence, it is also affecting the execution flow outside the function. So this can be exceptions, this can be nulls. as I have mentioned previously, side effects do not manifest themselves in the signatures of the functions. They are phenomena. They are phenomena that happens. So the compiler does not have any way to predict that they happen, and hence it has no way to warn us on compile time that we are about to do something bad. Hence, we need to keep in mind all the side effects that happen in the function, hence greater load on the programmer's mind, hence greater probability of bugs and undesired behavior. So, do you have any questions about the side effects? Okay, so let us have a look at how functional programming solves the problem of side effects. So the solution to the problem is actually the types that probably most of you already know. These are types like try, either, option, future. So the general signature, the general shape of this kind of types is f of a. They are higher-kinded types. So what are these types? Let us, for the sake of this example, call them effect types. And the main idea behind the effect types is to turn phenomena of side effects into data. So we reify the phenomena of throwing an exception or the phenomena of the capability to return null into a data structure that describes whether and how the phenomena has occurred. So, for example, if we are throwing an exception, this can be encapsulated in a try data structure. Let us have a look at how this works in practice. Here is the version of our previous example, but with the usage of this kind of effect types to encapsulate the phenomena of throwing side effects. So this is the method getUser from our previous interface that returns not a user like in the previous case, but an option of the user. So what is an option? It is a data structure that reflects that the method is capable of returning a null. Also, it is capable of containing the result value, in our case user, in the case where where null was not returned. So if the user is in the allowed range, we return a sum of user. Sum is a data structure that says that the result is available. It contains some extra information besides the result. So it does contain the result of user of ID, but it also contains the extra information, saying that no null was returned. Otherwise, if the user is not available, it is known. Known is also a data structure that contains some information, in this case that the user was not available, and in our case, no result type, no result, because the result is not available. GetPostOff is a new method that we will get to a little bit later. For the sake of this example, it is not needed. Connect. The original method of connect that establishes the connection to the database through an exception when the connection was not available, when the database was offline. In Scala, a natural way and standard effect type to reify, to encapsulate the information about the exception being thrown is a try. Now, try is a data structure that can be either a success or a failure. And if it is a success, then the exception was not thrown and the result is available. And if it is a failure, then this failure contains the exception that is to be thrown, but it doesn't throw the exception. So the point here is that the phenomena of throwing an exception is no longer present. Instead, the information about the phenomena that was supposed to happen is present in the data structure that is returned. So raw data, no side effects, raw data. Now let us have a look at how this plays out in the scenario when we first connect to the database and then try to get the user. So first of all, we establish a connection over here. In our case, it is simulated as connection false, so that it is supposed to fail, because false means the database is offline. And then what we do is we analyze the structure that was returned by the method connect. The structure is a try. Try can be either of two things, a success or a failure. So we have a match statement, and in case if it is a success, we have the access to the underlying user. So it is C, some customer C. No, sorry, not the user, but the connection. C is the connection C. And once we have the connection, we are able to execute the c.getUser on this connection. And then c.getUser returns a data structure with its own option of user. Then we examine this data structure. If the user is available, we print its ID. If it is not available, then we print an error that the user was not found. So let us see how this plays out. So in our case, the database was not online, so we have this error that database is offline. If we make it online, then we have the error that user was not found because we have specified that the user is with ID 10, which is not supported by our mock database. So how is that better than our previous solution of an imperative example? It is better because, first of all, we have no opportunity at all to get a null or to get an exception thrown. This opportunity is eliminated because, for example, database.connect that was supposed to throw an exception, now it returns a try. Second, we have no way to get beyond, to ignore the fact that this kind of opportunity of an error can happen on compile time. So if in previous case we could have just accessed the result of the function if actual database.connect right away via the connection variable, so the connection is the connection that was established. So here it is not possible because database.connect returns a structure try, and we cannot get to the connection object until we analyze the structure try that was returned, that explains the phenomena that happened within, and analyze the structure. So analyzing the structure means that we will need to deal with the phenomena of an error if this phenomena has occurred. This means compile time safety. You no longer have the opportunity to write the code that throws some exception and you forget to handle this exception. Because if you treat the connection over here like the database object and not a try of database, you will get a compile time error. It is reasonable. So to summarize what technique was used over here, it is the technique of effect types. The effect types reify the phenomena of side effects into data structures. So side effects are phenomena that the compiler knows nothing about, that just happens. And what we do is we turn the phenomena into a data structure. We make the compiler aware about it. Data structures are typed, hence we have all the power of the compiler to perform the handling of these side effects and to protect us against our forgetfulness, so that we do not forget that we need to handle side effects. However, you must have already noticed the problem with this approach. The side effects expressed in this kind of data structures, they do not compose well. Indeed, let us have a look at the following code, how we compose the side effects in a row way. So in an effectful database, in an imperative code, we had 3 lines of code to express the act of getting the database connection and then getting the user from this database. But over here in the database in a purely functional style, we first need to analyze each data structure and handle the possibility of things going wrong. This code looks much more ugly, and obviously we need to do something about it. Often this is the thing that scares people off some kind of high-level functional programming, this kind of ugliness that they see at first sight. So precisely what needs to be done to compose two structures like this, to compose the result f of a with a function a to f of b, so the function that acts on the result of the first computation f of a. What is needed precisely is to first unwrap the structure f of a, the first structure, and to access the result a. So maybe you have heard the analogy that monads are like burritos in some way, and this is precisely why. Because the effect types are essentially data structures that have the result value in it together with some other data. So you first need to unwrap the data structure and then act upon the information present in it, and only then will you get the access to the result values that you are trying to get the access to. So you need to unwrap this thing. After that, you need to act upon the information about the side effects, like I said. And if the result A that you are looking for is present, then you extract this result and do whatever you want to do with this result. In our case, it is composition with another effect in computation, side effect in computation. So you call the function A to f of b on this thing. Otherwise, you need to specify how to disrupt the computation gracefully. So, for example, if there is no result type, if it is an option that is known, or if it is a try that is a failure, then you need to specify how to gracefully exit from the computation. So this is the problem with the effect types. Does anyone have the question about the effect types method and the problem with it? Okay, then we will move ahead to the solution of the problem that naturally arises. Now, how many of you have a good understanding, can say that they have a good understanding of the concept of a monad? Can you raise your hand? Okay, great. Great, approximately half of people present. So here I would like you to focus on not on the definitions or mathematical specifications of the monad, but why it is needed. What is the motivation to why it is naturally called into existence by the style of pure functional programming? Well, first of all, what is a monad? The technical specification is that it has two functions. So a monad is defined for some effect type f. And it has two functions to work upon this effect type f. First is the flat map function that takes f of a as the first argument, and then a function of a to f of b as the second argument. So f of a is the first side effect that you are trying to compose, that you are trying to act upon. And the function a to f of b is the continuation. It is what you want to do with the result of this computation f of a. And pure is the ability to lift any value a to the context of f of a. Now, how it is needed in practice, what it does in practice. So we have already seen that the idea of composing two side effecting computations is pretty problematic because of the need to analyze the underlying structure. So what the monad does is it encapsulates away the details of analyzing the underlying structure. So let us get some more complicated example of composing side effecting computations to really see how it can be done easier with a monad. So here I have a slightly more complicated version of our previous example, this function over here. So what it does over here is that first it needs to establish the connection to the database, then it needs to get the user from the database, also side effect in computation. And finally, it needs to retrieve all the posts of this user with a given title from the database. It is also a side effect in action because obviously we might query the post that is not present in the database. So the way we do that over here is that we analyze every structure that we have. So the connection over here is an Ether string, which is an effect type that I have introduced to unify all the effect types that are present in this computation. So, for example, it is not very convenient to work under with effect types of option and try and some other effect type. It is not convenient when you have several effect types and you need to work under each of them. It is much more convenient to convert everything to a single effect type that expresses the needs of everything you have and to work under that effect type. So for me over here, this kind of effect type became either string of A. How many of you know the data type of either? Can you raise the hand? Oh, great. So an either is a data type that can be a data structure that can be either a left or a right. So for example, if it is a type of either of string and A, then a variable with this type can be either a string or an A. So why I am working under this type either of string and A? Because any computation that I am having here can be either an error, and an error can be expressed as a string of an error message, hence left of string, or some result A, when the error has not happened. So this is why I'm using this either string as an effect type. Every method that I have over here, the connection to establish the connection to the database, the def user to get user from the database, and this method with large signature over here to query the posts of a given user from the database. All these return an either of string effect type, meaning that either something can go wrong, in which case we need to report it as a string, or something can go right. And in this case, we will have an access to the result type, user or database or post. Okay, so the way it is done without monads, without anything from the cats world, without any type classes, without anything, any advanced techniques from the functional programming world, is that we need to unwrap every data structure that we are having to work with its result type. So for example, first we need to establish the connection to the database. We do that via the connection method that we have discussed earlier over here. It returns an either string of a database, which can be either right or left. And hence, we need to handle two cases. So if it is a left, we will, well, since we have the method of, since we have the large method returning either string of post2, then we, if the error happens in some of the data structures that we are trying to compute, we also need to return this error encapsulated in the left of message data type. But in case everything went right, we proceed to the next computation. So if we have connected to the database successfully, we proceed to getting the user from the database. If that succeeded, we proceed to getting the posts of the user from the database. Now it is very cumbersome. And this is where monads with their flat map come in. So the code that I have displayed over here can be expressed like this with the monadic flat map function. So flat map takes care of handling of all these details about how to unwrap the data structure and what to do in case the data structure is does not have any result type, and how exactly you should pass the result type from the data structure to the next computation. So in Scala, there is even a shorthand for this flat map computation, the so-called monadic flow. So this for statement over here is another way to express the computation above. So in this manner, in this kind of form, it is much more similar to the concept of the original imperative solution. So here we have also two lines of code to establish the connection and one to print the user information. And here we also have two lines of connecting to the database, of getting the user, and then finding the post with the given title of the user. So the key thing to remember here is that the monad takes care of unwrapping your effect types, of analyzing them, so whether exception happened or not, whether an error happened or not, whether something was null or not, or maybe whether the computation succeeded, and the result was returned successfully. So the monadic flat map function takes care of that. It abstracts away these details of analyzing this data structure so that we can write the monadic flow as if it was an imperative code. However, the monad takes care of everything, of how to analyze this stuff. So this was about the monad solution in particular. Does anyone have the question about this section about the monad? Okay, so we will proceed to the type class pattern. So a monad can be viewed as a set of tools to work upon the effect type data structure. So if we are programming this way, this functional way, if we are programming the way that we reify the side effects that happen within functions, if we remove these into data structures, then it is natural that we need specific tools to work with these data structures. And the monad is only one of these tools. It answers on the question of how to sequentially compose two computations that are side effecting and express their side effects as effect types, effect data structures. So the monad answers this question. But it is natural that there are much more problems to functional programming than sequential composition. So for example, it is parallel composition, to which we will get a little bit later. And it is natural that a similar set of tools, set of methods, is needed to work around every such a problem. And it is not given at all that this kind of set of methods will be available by default on the data structures that you are programming against. So over here, for example, this flat map method is natively available in the Scala implementation of Aether. Well, great, but if we take this proposition that we might need much more tools to work with these data structures, and these tools might be defined by the projects, by the context in which we are using these data structures. So we might not even be able to predict which tools we might need on definition time of these data structures. If we have this situation, we need a little bit more open world assumption. We need to be able to define new tools dynamically as we go. We need an ability to inject new methods into existing data structures. And this is where the pattern of a type class comes in. So please raise your hands who are familiar with the concept of a type class. Okay, great. So just to remind, the type class pattern consists of the following parts. So first of all, you need to remember that it is defined for some data type. For some data type that, for the sake of our argument, is an effect type, and it encapsulates some data about some effects that could have happened, and you need tools to analyze these effects. So a type class is a toolbox defined for a certain data structure. Like, for example, for a log of wood, you have a toolbox with a saw, a hammer, nails. Same way for certain effect types like Aether, like options, like whatever. We have certain toolboxes that are suitable for these effect types. They are defined in a trait. So every tool is a method of the trait, which is a type class. So toAether string, for example, is a type class that is supposed to inject a method that will convert some effect type f. It is defined for to the type Aether of string and a. Now, why is that needed in our project? It is needed because I have mentioned earlier that we need to work on one effect type only. Because if we have option, future, try, Aether, if you work against all these effect types at once in one project, it quickly gets confusing. We need one effect type. And in our case, it is Aether of string and a. And in order to convert any effect type that we might encounter into this common denominator, so-called, we need a type class that will inject a method called toAtherString into option, into try, into whatever. Now, how exactly it happens? So we have a companion object over here, and in the companion object we have, first of all, we have this rich wrapper pattern. The rich wrapper, it is an implicit conversion from f of a to this class ops, which has toAtherString method defined on it. Now it is a standard rich wrapper pattern. It's the same way Scala converts any string to a collection, injects the collection methods to a string in the exactly same manner via this rich wrapper pattern. But there is something special about this rich wrapper pattern because it has an implicit dependency on our toolbox, toAtherString. So basically what this rich wrapper says over here is that we can convert any effect type f of a to something that has this toAtherString method defined on it, given that we have a toolbox toAtherString of f defined on this data type. And we have two implementations of this toAtherString toolbox, so one for option and one for try, because we are dealing with option and try in our project. So the effect of it all is that in one of our examples, I was able to use toAtherString method on the database.connect method, which, let us recall briefly, which returned a try of database. So I was able to use the method of toAtherString, which is not originally present in this try data type. I was able to use this method I was able to inject this method into this thing. Now, this is the main idea behind the type classes. So, for example, if you like the idea of monads and you have a data structure that originally does not support the flat map method, but you know how to implement it, you are absolutely able to inject this flat map method or to simulate the injection of this flat map method using the type class pattern. And in fact, it is natural that if we have the situation when we have a lot of tools that we might want to implement for a lot of data types, and they all conform to the same pattern, which is just a trait with the set of tools available on the data type. If we have this situation, it is natural to define them as a separate library. And one of such libraries is cats, that is currently trending in the Scala community. So, for example, this is how the monad type class is defined in the cats library. So it is a simple trait with abstract methods called flatMap, pure, Taylor recursive, monadic. Taylor recursive monadic is to make recursion, Taylor recursion with monads. So flatMap is a sequential composition, but what if you have a loop of sequential compositions? If you have an entire loop of sequential compositions, you will have to define that, to express it using monads. So here you may already notice the situation when the monad, the type class that cats defines, has a method that is not natively available in any of the Scala core data types. So you will not find the Taylor recursive monadic method within option or try or Aether that are native Scala representations. The only way you can get this is via cats type classes. The structure of the library, how is it structured? So it contains several packages. Main package is the cats package, which contains all the type classes that cats provides. So, for example, we have just seen the monad type class, but other type classes are also available. So, for example, if we have time, we will have a look at the Cartesian type class, which is well, they have removed this type class in the later versions of cats, but since we are using an older version, there should be no problem in our project. So the point is that there is an entire library of, okay. Okay, so it seems that we are running off time, so I'll skip quickly to the end. So the point to remember about the type classes is that they can be treated in two ways. First, they are toolboxes for the data types that express events, that express effect types. And second, they are injectable interfaces. So they are bunches of methods you can inject into other data types or simulate injection. So let us quickly summarize what we have discussed so far. So first of all, we have discussed that side effects are bad because they increase the mental load on the programmer and hence more bugs. Second, effect types are reified into effect types are solution to the problem of side effects because they turn the phenomena of side effects into data. They express the possibility of an exception with a data, either success or failure. Next, when working with effect types, we quickly encounter the problem that we need to analyze the structure each time, the structure of the effect type. Each time, we need to do something with the result of the computation. And this poses a major problem for readability. And it is solved by type classes. One of these type classes is a monad, which answers the question of sequential composition. And finally, there are entire libraries of type classes. One of such libraries is cats. So here are the resources that were used in this presentation. So first of all, the presentation. Second, the code is available on GitHub. And finally, if you are interested in functional programming, in pure functional programming, our company Functor Hub specializes on educational materials, private trainings, and consultancies. So you are also welcome to contact us. So thank you for your attention, and do you have any questions? With cats? Well, in fact, there is an implementation of our databases, of our sequential database over here that precisely uses cats. So as you can see, the cats code is precisely the same as the native Scala code when given when it is a monadic flow, but with one difference that we are able to use these cats imports to define more, to work with cats. And second, obviously you are not only using monads in your pure functional programming. Very quickly you will hit other problems other than just sequential composition, and this is when the native Scala core will not be able to help you and you will need cats. Mm-hmm.
In the monad interface, we saw that there are a tailorec-m method. Should it be called explicitly, or it calls it implicitly by itself? For instance, on tailorec annotation or something like that.
No, it is called explicitly. You must use this monad.tailorec-m of blah 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 syntax.
Do you have any experience of using the cats in the Gradle project? Because there is a plugin for SBT, and you need to add a plugin for SBT project, but we don't have this plugin for Gradle, or we do.
With Gradle? Oh, yeah. No. Well, but actually you can use cats with Gradle with no plugin. The plugin was needed for earlier versions of cats that did not support, or not cats, but Scala that didn't support some of the type level features. And currently, if you're using Scala 12, it should be okay. I see. Okay, if there are no more questions, then thank you for your attention.